In today's video, we are going to talk a lot about inorganic chemistry. This is the inorganic chemistry marathon video. Let's analyze what are the questions they have asked in past years and how it differs from January attempt, right? In January attempt, you see there are more statement-based questions were asked. And also it focuses on a little bit of P block of 15, 16, 17 and more about D block and coordination compounds. Okay. And what are the things you have to do is to understand the concept, why that is happening, and solve more problems on it so that you will get a hang of the questions, what kind of questions can be asked. We have released top 250 questions on inorganic chemistry. You can check that out if you want for an extra revision. In today's chapter, we are going to discuss these things: periodic trends, P block elements, DNF, and coordination complexes. Okay, so without any further delay, let's get started. Periodic properties, let's quickly go through those properties and the exceptions based on it. S block element, P block elements, wherever the electrons goes and occupy, those are the corresponding block elements we call. And then periodic trends. Atomic radius decreases across the period and increases down the group. And the key point you have to remember that is lanthanide contraction. Due to lanthanide contraction, decrease in size from lanthanum to lutetium because of their poor shielding of 4f orbitals, 4f electrons. And same thing happens for actinides as well. So which will lead to second and third transition elements are similar in size. This can be asked as a statement based question. Zirconium and hafnium are similar in size. Niobium and tantalum are similar in size. Then atomic radius slightly increases from 3D to 4D series. Then it remains nearly same from 4D to 5D series due to this lanthanide contraction. If you want this notes, just put it in the comment section. If I get more comments on that, surely we will release it. Then ionic radius, remember this thing, cation, that is smaller in size, then comes neutral atom, then anion. Always the anion part which is larger in size. Okay, there you have to know about isoelectronic spaces which is having same number of electrons, right? So talking about the sizes in isoelectronic series, the size decreases with increase in nuclear charge. For example, you can see oxygen 2 minus, that is bigger, then comes fluorine, sodium plus, magnesium 2 plus and aluminium 3 plus. Sizes decreases with increase in nuclear charge, which there is a simple reason which can hold all those electrons together, so the circle will be smaller, right? Radius will be smaller. Then ionization enthalpy, it increases across the period and decreases down the group. The important exceptions in the ionization enthalpy is that beryllium is having more ionization enthalpy than boron. It's because beryllium, which is in 2s2 configuration, and boron, that is having only one electron in 2p, which can easily removable. The same thing applies for nitrogen and oxygen also, but here nitrogen is having half-filled configuration, which is more stable than the partially filled. Partially filled means 1, 2, 4, 5, right, in p orbitals. Those are partially filled. So always remember, fully filled, which is more stable, then comes half filled, then partially filled. Magnesium is greater than aluminium is because of stable 3s2 orbital is there in magnesium, then in aluminium we have 3p1. Phosphorus is greater than sulfur because of the half filled 3p3 stability. Okay, then as you can see here, sodium, which is having small electron ionization enthalpy, first ionization enthalpy, but IE2 of sodium, that will be bigger because it reaches the noble gas configuration after removing one electron from it, right? So remember that point while doing the problems. Then electron gain enthalpy becomes more and more negative across the period, so which means it increases in the period and decreases down the group. The exceptions of electron gain enthalpy are chlorine is more than the fluorine because most electronegative electron gain is for chlorine. Because of this small size of fluorine causes the electron-electron repulsion. Okay, very important point. Then comes noble gases. Noble gases usually will have positive electron gain enthalpy because that is already full. It is not at all hungry, right? It's completely full. Then nitrogen is having less electronegative than expected. It is because of, again, the same reason, half-filled stability. The trends of group 17 follows this order. Cl is greater than fluorine, then comes bromine, then comes iodine. Okay. Then electronegativity. Fluorine is having more electronegative than others. That is highest electronegative atom in the periodic table. The trends follows like this. It increases across the period and decreases down the group. Order you can see over here, and importantly, noble gases are not having any electron gain enthalpy because that doesn't want the electron, right? No compounds typically, and cesium, which is having lowest, that is 0.7. Then comes valence and oxidation states. So whenever we are calculating the valency, the maximum valency would be the group number up to group 14. After that, it decreases. 15th group will have a valency of 2, 16th group will have 2, 15th will have 3, 16th will have 2, 17th 1, and 18th, of course, noble gases, so the valency is 0. And down the group, there is an important effect called inert pair effect. Inert pair effect means it doesn't want to give up the s orbital electrons, right? The stability of the lower oxidation state increases down the group. For example, here you see thallium plus 1 is more stable than the thallium 3 plus. This point were asked many times in the examination. This is an exceptional case, so please remember that. Then lead 2 plus, that stability is more than lead 4 plus. Bismuth 3 plus is having more stability than bismuth 5 plus. Okay, if they are asking for the reason in assassin reason type, then inert pair effect is the reason. Then comes metallic and non-metallic character. Usually it decreases across the period and increases down the group. We very well know sodium is in the left side, and all those non-metals are in the right side. Here the diagonal relationship, lithium and magnesium is having similar properties. Beryllium and aluminium, boron and silicon is having similar properties is due to which will have similar size and electronegativity, which will lead to the very similar properties. Almost many 15-16 properties were similar. This is about periodic properties. Then let's quickly go through p block elements. In p block elements, we have boron family first: boron, aluminium, gallium, indium and thallium. Here comes the inert pair effect, remember that. And oxidation state, +3 oxidation state would be more stable, but due to the inert pair effect, +1 of thallium is more stable than the +3. Talking about boron, usually remember that the first element of the group which will have different properties. Okay, boron, carbon, nitrogen, oxygen, these will have different properties from the rest of the same family. Okay, so whenever the questions were asked including these, think twice before answering. Okay, then talking about the boron behavior, it is the only non-metal in that group, and it will have highest electron negativity and ionization enthalpy. It forms the covalent compounds. Other compounds like aluminium and thallium, they are forming ionic compounds, but here boron is forming a covalent compound, and this is an electron deficient compound which will have incomplete octet. B2H6, you remember, PH3, which will have the vacant orbital in it, right? Then boron compounds, these are some boron compounds. Just go through it, even though they may ask you in JEE Main, but definitely they will ask you in JEE Advanced. But these are also important for your JEE Mains. Borax, the formula Na2B4O7 10H2O, which will be used for analytical chemistry, and boric acid H3BO3, it is a Lewis acid and which is a weak monobasic acid, okay, and used as an antiseptic. Then important compound diborane, which will have 3 center 2e electron bonds, banana bonds we will call it. You remember BH, B, these two bonds. Which bonds? These bridges. Not the terminal one, this part. This part which will have three compounds sharing in, three elements sharing in two electron in it. That's why we call it as a three-center through electron bond, which is also Bernoulli bonds, which are highly reactive. Then aluminium, that is amphoteric oxide. The oxide of aluminium that is amphoteric in nature, that is an important point. Then other reactions of aluminium includes it reacts with HCl. Due to this amphoteric nature, it acts as an AlCl3 will be formed, and H2 gas it releases. It can act as an it can react with any OH also to release H2 gas. Okay, then reactivity, it forms a protective oxygen layer. Passivation happens in aluminium and chromium. Okay, chromium also forms this oxidation layer, not reacts with oxygen, and aluminium also forms the same, which is a very important property of aluminium, amphoteric in nature and passivation, super important. Then it reacts with N2 to form AlN at high temperature. Then group 14 elements, carbon, silicon, germanium, tin, lead. Again, inert pair effect speaks for this lead 2+ is more stable than the 4+. The common oxidation states are +2 and +4. Lower oxidation state predominates down the group. And then catenation. Catenation is an important property of carbon family, especially carbon. That is how the whole organic chemistry were born. Right? So carbon is having more catenation property. It can form an n number of bonds. Then silicon, germanium, tin and lead. Okay? And carbon-carbon bond is the strongest too. Then allotropes. Allotropes of carbon are diamond, graphene, fullerene and carbon nanotubes. The important allotropes. Diamond, which is these points are also important. Whatever I have written over here, those points are super important. Those points were asked many times. Okay. sp3 3D network, and which is hardest, which acts as an insulator. But on the other hand, graphite, that is sp2 hybridized, its layer soft and conducting electricity. It's because of there is a free electron in graphite. Okay. And fullerene, that is, it can be of C60, C70. Fullerene will have this hexagon and pentagon structure alternately present over there, right? C60, which is called Buckminster fullerene. Then how many, you can just check it out, how many hexagons are there, how many pentagons are there in C60. Okay. Then carbon nanotubes, which is a rolled graphene sheets, which is used in many fields. And other important compounds of carbon is carbon monoxide, carbon dioxide, carbon monoxide, which is isoelectronic with N2. Many times that was asked. And which is in reducing agent, we linked it with metallurgy. Remember? Then, which is poisonous in nature, it binds stronger with hemoglobin than the oxygen. That's why carbon monoxide inhaling is very dangerous. It is harmful. And then it forms metal carbonyls. We see that in coordination complexes. Also, there is a synergic bond formation. Back bonding happens over there with the carbonyl ligand. Then comes carbon dioxide. It's a linear sp2 hybridization. sp hybridization happens. Dry ice means which is solid CO2. This is a greenhouse gas. And carbides, that is ionic in nature. How it is? It will react with water. It will form calcium hydroxide and acetylene. Okay. Then carbides are, acetylene gas is very important for the ripening of fruits, that application. Then silicon carbides, that is carborundum. It's very hard. That is covalent in nature. Silicon dioxide, 3D network solid, acetic oxide. Like it forms quartz, cristobalite, diamite. These are the other forms of silicon dioxides. And silicones. Silicones are not much important for the JEE Main. You can just see it, see the questions or just have this information. And zeolites are the 3D aluminosilicates, which is microporous, ion exchange happens and acting as a very good catalyst. Then comes nitrogen family. Nitrogen family, nitrogen, phosphorus, arsenic, antimony, bismuth, NS2NP3 configuration. The oxidation state ranges from -3 to +5, and the stability of a +5 decreases down the group because of the direct inner paraffin. And nitrogen shows -3 to +5 oxidation state. Someone have asked in the comments, nitrogen do exhibit variable oxidation states? Yes, it is. Okay, look at the electronic configuration of nitrogen. That is 1s2, 2s2, 2p3. It can lose all 5 electrons or it can gain 3 electrons, right? So, which can exhibit variable oxidation state. Bismuth shows mainly +3 oxidation state. And allotropes of phosphorus, again, white phosphorus, red phosphorus, black phosphorus are important. Just to know about these things, not much questions were asked, but white phosphorus, which is very poisonous in nature, and that is tetrahedral in structure. Okay, white phosphorus, that is tetrahedral in structure. Then hydrates, super important. The trend of hydrates, ammonia, phosphine, ASH3, antimony hydrate, and bismuth hydrate, which has it is a decreasing trend, decreasing stability, and the bond angle is given over here. The basicity of hydrates and the reducing character, that is also arranged. Okay. Then talking about ammonia, sp3 hybridization happens, pyramidal in shape, which will have 2 lone pairs, so that is an base. And Haber's process, ammonia can be prepared from N2 and H2 with very high temperature and very high pressure condition, because nitrogen is having triple bond end, right? Which is basic in nature. It can form a complexes also. Oxides of nitrogen, N2O, NO, N2O3, and what are the oxidation states of it? And N2O3, NO2, N2O5. Okay, these are acidic oxides, okay, which are important. Then NO is having an odd electron molecule, and that is in paramagnetic. NO2, that is a brown gas, dimerizes with N2O5. And N2O, that is nitrous oxide, that is a laughing gas, which was used as an anesthetic. Okay. Then nitric acid, through Alstra's process we can prepare this nitric acid using a platinum as a catalyst at very high temperature. Ammonia treated with oxygen to form NO, NO with oxygen forms NO2, NO2 with water, it gives nitric acid. Then we have properties of base groups. Strong oxidizing agent, reduces to NO2, NO, N2O, etc. And it passivates iron. I told you, right, it forms a protective layer. Mostly iron won't be forming. Chromium and aluminium forms a very good protective layer on it. Iron which will react if we have oxygen and water with it. Aqua regia, that is three parts of HCl and 1 part of nitric acid in it. It reacts with metal. Copper reacts with dilute nitric acid to form copper nitrate and NO gas. That is important. That can be asked as a question. And with concentrated nitric acid, copper forms NO2 gas. Okay, that is the difference. Then phosphorus compounds. Phosphine, that is super important. It is a poisonous garlic smell gas, less basic than ammonia. And these are some phosphorus halides. PCl3, which is sp3 hybridized and pyramidal in shape. These things you can get it from chemical bonding VSCPR also. And in solid state, PCl5 goes as PCl4 plus and Cl minus or PCl6 minus. Okay. Upon hydrolysis, PCl3 forms H3PO3 and PCl5 forms POCl3 and HCl. With more amount of water, excess amount of water, it will form H3PO4. Okay, complete hydrolysis happens over there. And these are the oxides of phosphorus, hypophosphorus, phosphorus oxoacids, and orthophosphorus acid. What is the basicity? This part and this part is important. Okay, basicity is a number of OH groups present over there, not just an hydrogen atom. Okay, the hydrogen must be attached with the oxygen, more electronegative atom. Okay, then group 16. So group 16 elements, we have oxygen, sulfur, selenium, tellurium, polonium, and the common oxidation states are +2, +4 and +6. -2 is the most common oxidation state. Oxygen mainly shows an exception because of course that is the first member of the group. It shows +1 with the fluorine, right? With fluorine it shows +1 because fluorine becomes more electronegative. Oxygen will act as a positive part there. Okay. Then peroxides it can form and superoxide it can form with then -1 and -1/2 oxidation state. Sulfur to polonium it shows +4, +6, and as we increases moving down the group, the higher oxidation state gets stable. Then oxygen can exhibit in two different states, two different allotropes, that is dioxygen and ozone. This structure of ozone, that is diamagnetic bent, and it is a powerful oxidant, many times used in organic chemistry, right? Ozonolysis. And O2, that is paramagnetic in nature and that is diidentical. Ozone turns potassium iodide paper to brown, which is an indication of the liberation of I2 gas, and in purification purpose and bleaching also ozone is used. And the bond order is 1.5 over there. Sometimes the question can be asked from ozone structure also. Okay. Then allotropes of sulfur, rhombic sulfur, monoclinic and plastic. These are not much important for your JEE Main, but you can just take a note of it, just go through it once. Then hydrides of group 16 elements. The stability of the hydrides, there was some statement based question were also be asking for the reason behind the stability of the hydrides. It's because of the decreases the MH bond strength, right? Metal to hydrogen bond strength, which is getting decreases. It's the reason for this decrease in stability. And talking about the acidic strength, the reduced bond enthalpy makes the proton release very easier, and the reducing property increases from oxygen to tellurium. It's because of the thermal stability. Okay. Then hydrogen peroxide. Hydrogen peroxide is a special compound. You must have seen that in volumetric analysis as well. It reacts somewhat different to calculation part. This is having a non-planar structure, which is an open book structure, which will look like this. Okay, then OO bond exists over there. In the preparation part, sulfuric acid with barium oxide produces hydrogen sulfide with barium sulfide. It is a laboratory preparation, and industrially it is prepared from 2-ethyl anthraquinone, gives anthraquinone with peroxide. It is acting as a very good oxidizing agent and reducing agent with the strong oxidants, and stored in with stabilizers. And the volume strength, that is stain volume, which will be 3% of it. We saw that in redox and all concepts, right? Sulfur dioxide preparation is very simple. Sulfur plus oxygen gives sulfur dioxide, and it reacts with sulfuric acid. Copper reacts with sulfuric acid to form copper sulfate, sulfur dioxide. Through that method also we can prepare. The properties of sulfur dioxide involves this Fp2 hybridization. This is a V-shaped compound. It is an acidic oxide, and that is having a acting as a reducing agent as well as the oxidizing agent. It acts as a temporary bleaching agent. Okay, because of this reducing property. Then sulfuric acid, very important acid. It is prepared through contact process. Okay. So, in contact process, first two steps we already know in Lee-Chatelain principle also. And sulfur dioxide reacts with sulfuric acid. Okay, this step is a bit different. We are adding sulfuric acid to produce sulfuric acid. So sulfur trioxide, we are adding sulfuric acid to form oleum. From oleum, we are adding water to form sulfuric acid. Okay, so why we can't form it directly? Because that is more explosive. Okay, then which is called king of chemicals? It is a dibasic acid, H2S44, and pKa, that is -3, which is a strong acid. It acts as a dehydrating agent, we very well know that, and acting as an oxidizing agent. Hot concentrated sulfuric acid acting as very good oxidizing agent. And with metals, it acts as an acid, as in dilute state, and with concentrated state, it acts as an oxidant with the evolution of SO2 gas. Then group 17, halogens, fluorine, chlorine, bromine, iodine, and astatine. Here in halogens, the color and boiling point, which are all given. Other than that, the reactivity, we know fluorine is more reactive than chlorine, then comes bromine and iodine. Bond dissociation energy. I told you before, fluorine is very small in size. Okay, so which will lead to, if I am adding more electron to it, that will do the repulsion. So the bond dissociation energy, it's bit varying from others. What we are expecting. Fluorine, then comes bromine, then fluorine, then iodine. Oxidation states, fluorine, it's exhibit only -1 state. Other halogens can do other oxidation state like -1. In addition to that, we have +1, +3, +7, +5 also. Right? Because fluorine is correct. Most electronegative among the elements in the periodic table. Then fluorine is most reactive also. Oxidation power is so just general F2Cl2, Br2 and I2 in the decreasing order. It can undergo displacement reactions as well. In halogens, we have this halogen hydrides or hydrogen halides. Okay, not hydrides. It itself is negatively charged. So, which makes hydrogen halides. So, trends follows from HF to HI. These are the trends for thermal stability, bond length, bond strength, acidic strength, and reducing power. Once again, heads up guys, if you're watching this till now, if you want notes, let us know in the comments. And HF, that is an hydrofluoric acid, that is an weak acid. Hydrogen bonding is there, high bond strength, it attacks the glasses. So which is not stored in the glass container, which is stored in plastic or wax containers. That is an important property of HF gas. Then chlorine produced using decon process, where CuCl2, carbon chloride, is acting as a catalyst. And chlorine can react with alkali to form sodium hypochlorite, and hot concentrated alkali, it will give sodium chloride, NaClO3. Chlorine will have this bleaching property. It's because it reacts with water to produce this nascent oxygen, the single oxygen atom. Okay, that will act as a bleaching agent over there. It just whitens. Then hydrochloric acid, which can be prepared by treating salt with acid to produce HCl, or H2 plus Cl2 can also give HCl. In the properties, it is a strong acid which can be completely ionized, right? It reduces MnO2 and KMnO4. See, look at the reduction. MnO2 reduced by HCl, which is from +4 oxidation state to +2 oxidation state. Chlorine goes from - to 0 oxidation state. And aqua regia, I told you 3 part HCl and 1 part nitric acid, which reacts with gold to form auric chloride complexes, which is a metallurgically important step for the separation of gold from its ore. Oxo acids of halogens and its oxidation states are also given, and the acidic strength. Acidic strength increases with oxidation state. This point is super important. So many times it was asked. Decreases with oxidation state, oxidizing power, acidic strength increases with oxidation state. Important oxides, important acids of halogens, that is HOCl, HClO4, HiO3 and H5IO6, periodic acid which oxidizes glycol. Then interhalogen compounds. Heavier halogen bonds within lighter halogen to form this kind of compounds like ClF3, ClF, ClF5, IF7. It is an highest one. IF7, that is an halogen's highest oxidation state, +7 state. Okay. Then the properties, they can be asking question about the structure of these interhalogen compounds and the hybridization part. Talking about the application, it is useful in fluorinating agents and more reactive than their halogens. Okay, that is an important point. Then noble gases. Noble gases are generally inert, that's why inert gases. They are colorless, odorless, tasteless, and which will have low melting and boiling point, and helium has the lowest boiling point of all the metals, which is 4 Kelvin. Think about it, boiling point itself less than the water boiling point, water freezing point. Okay, so that is having very lowest boiling point. It is inert because of the completely filled valence shell, and which will have the highest ionization enthalpy. There is no electron gain enthalpy, that is 0 for inert gases. Xenon only can form the compounds because it is so big, the outer electron shell, that can lose the electrons to form the compounds like xenon fluoride compounds. The question can be asked from again structure and hybridization from the xenon compounds, and the important reactions is also given. Okay, and the hydrolysis property of xenon fluoride, xenon F2 forms HF and O2, F4 forms XeO3. Sometimes this question, reaction kind of question, A is reacting with this, B to form this, what is the B, what is CD, that type of question can also be asked from this part. And the uses we very well know. It is used in balloons, cryogenics, lasers, photography, and etc. Then we are getting into important part, that is D block elements. In D block elements, scantium to zinc, we have the electrons, incoming electron goes to D shell. There are two exceptions in 3D series, that is chromium and copper. By the time you know everything about this configuration, I'm not going to in detail about this. And atomic radii decreases from scantium to manganese, and then slight increase will be there. And poor shielding of the d orbitals is a reason, and Lagrange contraction effect happens over there in inner transition elements like 4D and 5D series, which will lead to the similar radii. Then metallic character, these are all our metals having high melting and boiling points. All those metallic properties applies over here. And the melting point order is chromium, molybdenum and tungsten, which will have the highest unpaired electrons in the metallic bonding. And we have oxidation state. Scantium, titanium, the variable oxidation state, maximum oxidation state is also listed over here. Then the key points you have to remember here, that is the maximum oxidation number is a group number, right? After manganese, the maximum oxidation state decreases, and the most stable one is +2, +3 oxidation states. Manganese only shows +7 oxidation state. Magnetic properties, paramagnetic means unpaired electrons are there, diamagnetic means unpaired electrons are not there. Right. So if that is paramagnetic, we can calculate the magnetic moment by using the formula square root of n into n plus 2. N refers for number of unpaired electrons. For example, here you see Fe2 plus, that is having 4 unpaired electrons, right? 3d6. So 1, 2, 3, 4, 5, 6. So 4 unpaired electrons are there. Look at the value which starts with 4. 5 unpaired electron means the value will start with 5. Similarly, for 1 unpaired electron, 2 unpaired electron, 3 unpaired electron. So how much of an unpaired electrons is there, that will, the value start with that number. You need not to calculate the square root of those things. It's not necessary. Okay. So that is a simple trick you can remember. And all electrons are paired in zinc 2 plus, copper plus and scantium 3 plus. Talking about the unpaired electrons, if there is a completely filled configuration or no electron in the d orbital, then there is no dd transition, right? The electron jumping, the playing with electron is not there. right? So which means that those are colorless. Other than that, if I'm having only one electron also, that becomes colored. Like you see, titanium 3 plus, it is purple in color, vanadium 3 plus. So we already posted how to remember these colors in the simple trick. If you, by that time you might have your own way of remembering it. If you do so, then get a hang of it, solve more problems on colors. Because from NCERT table, the colors question can be asked. That is super important. Okay. Or else you can take a screenshot of it. What are the colors for what element? Remember, completely filled and no electrons on d orbital means colorless. Okay. Then catalytic property. It provides the signs for the reactant absorption. The variable oxidation states facilitate the electron transfer. Basically, it is acting as a platform, right? Like a train station, to people can come and take a train, or people can go and take a flight, like an airport, like a train station. Catalysts are acting like that. Okay, iron, V2O5, nickel, platinum, palladium, manganese, and mostly these transition elements are very good catalysts. Okay. And complex formation, there are some empty orbitals, of course. It is having d orbital, that is big. So which will have empty space where the electrons can come and occupy, which means it can form a complexes, right? So because of the size of the cation, charge and availability of the d orbitals, it can form a complexes. That is our next chapter to have been formed, that is coordination complexes. Then interstitial compounds. These transition elements, these metals can bigger in size, right? Compared to other small elements like a hydrogen, nitrogen or carbon, these are bigger in size. So what can be happen over there is the inner space can be occupied by the smaller elements. That is what interstitial compounds are. Okay, so that is how this TiH 1.7, VH 0.5. So those are small compounds and those were arranged differently. These interstitial compounds will have high melting point, which retain the metallic property, that will be remain intact, and this is a hard, the properties will be same, but only the difference is this will have different oxidation state, and there will be defects. Okay, if you know about this solid state, defects will be formed, right? That kind of defect we can see in interstitial compounds. And alloy formation, the similar atomic radii allows the substitution like brass, bronze, steel. Why the alloys we are producing alloys? Because that is more economically effective way of using it. And if I am using iron for a vessel, then that will corrode easy. Because of that, we are mixing it with other metals to form an alloy so that we can use it as a stainless steel. Okay, then these are the important two compounds, two heroes of D block element, that is potassium dichromate and KMnO4. The questions can be asked from this part a lot. From the preparation till the structure, hybridization, and what is the oxidation state changes in the reaction. So many questions can be asked from this part. Look at the reaction, how it is prepared, and the structure. Two CrO4 tetrahedral sharing one oxygen atom, which will look like this. Cr forms a compound like this, which will have Cr2O7 2 minus. Okay, and Cr in the +6 oxidation state, which will act as a very good oxidizing agent. It is an orange crystal that acts as in acidic medium +6 to +3 oxidation state it goes, and then chromate and dichromate can maintain an equilibrium. In acidic medium, dichromate predominates, and with basic medium, chromate predominates. Okay. Then oxidation reactions of potassium dichromate, FeSO4, reacts with this oxygen evolved from the first step to form ferric sulfate. Those kind of oxidation can happen over there. And then another important reaction which we saw, that CrO5 formation, CrO5 reaction, that is taking in butterfly shape. That series of reaction, we are so many times we have solved those type of questions in our block elements, inorganic chemistry, important questions. Those video you must have aware of it. That part is also important here. Then it is used in the volumetric analysis and leather tanning and oxidizing agents. Then talking about potassium permanganate. Potassium permanganate, which can be prepared from pyrolusite MnO2 using a fusion with KOH, electrolytic or chemical oxidation method. And more importantly, the structure of permanganate, that is tetrahedral in nature, which will look like this. Mn, this is tetrahedral, right? MnO4 minus is there. So double bond O with the minus charge. And Mn, which is in +7 oxidation state over here, and it is deep purple in color due to charge transfer. Sometimes the question can be asked, manganese is also in the D block elements, right? So why that is color? Usually we tend to answer, okay, DD transition. No, that is not DD transition, that is because of the charge transfer. Okay, the color is due to charge transfer, which is super important, remember that. Then the next important part in permanganate is that in acidic medium, what is the change? Neutral medium, strongly basic medium, what is the change? In oxidation state of the manganese. So look at this, +7 to +2 oxidation state, +7 to +4 oxidation state, and +7 to, this is manganate it is formed, so which is +6 oxidation state, right? So that oxidation changes, which is super important. Then other important reactions, what happens in the acidic medium, and with the oxalic acid, what type of reactions are produced, those are also important. They won't be asking much in JEE Main, but better to know about these concepts if you have time. And alkaline medium, the reaction is given over here. Manganate is green in color. Okay, and the decomposition of permanganate on heat, which will form K2MnO4 and MnO2 plus oxygen. Okay, kind of in this disproportionation it happens. It forms in two compounds while decomposition. It kept in dark bottles because it decomposes in sunlight. It's not a primary standard, which contains MnO2 as an impurity. Okay, in K2Cr2O7, we told that is used as in volumetric analysis as a primary standard. But in KMnO4, sometimes it is not used as a primary standard because of the impurity present over there. Okay, then test for Mn2+, that is from analytical salt analysis part, which is treated with lead oxide and HNO3 to form a purple color solution. So this is a quick chart of comparison of KMnO4 and K2Cr2O7. You can just take a screenshot of it. Then we have F block elements. F block elements, we have actinides and lanthanides. The most important part over there is lanthanide contraction. Why that is happening? Because of the poor shielding of 4f electrons, and some important lanthanide configurations are given over here. Lanthanum, cerium, gadolinium, lutetium, because that can be asked as a questions. We solved it a lot in block chemistry. About the oxidation state they may ask, about the stability of the ions they may ask. Okay, talking about the ionization enthalpy. Why this is having more, why this is having less. So to know that, you have to know the electronic configuration of important lanthanides. Okay, europium, cerium, ytterbium, terbium, these are some important lanthanides to remember. And +3 is the most common oxidation state, +2 and +4 can also be exhibited by some elements. The stability pattern follows like this: europium 2+ and ytterbium 2+ is half stable because of half filled and completely filled, and cerium 4+ and terbium 4+ is also stable at +4 oxidation state. And these are acting as a very good redox behavior, also acting as a good reducing agent, good oxidizing agents. And lanthanide contraction, I told you. What is the consequence of lanthanide contraction? Okay, there is a atomic radii decreases. Due to that, what will happen? Okay, atomic or ionic radii decreases. Due to that, some elements will have similar properties, right? It is difficult to separate those elements then, and extraction by ion exchange, which will make difficult, and the basic strength decreases. That is a very important point, very important consequence of lanthanide contraction. Look at cerium hydroxide and lutetium hydroxide. Cerium becomes more basic in nature than the lutetium because that becomes smaller. So smaller means more covalent of MOH bond, which means less basic. And second and third transition elements are having the similar ionic radii, like zirconium and hafnium, niobium, tantalum, molybdenum, and tungsten, right? So this consequences are super important. Then colors of the ions. Once again, the NCERT table, if you have those colors were only asked. Here the color is due to FF transitions. These are the important colors of lanthanides. And as usual, the cerium 3+ and the ytterbium 3+ are colorless, which are not expected. And other than this, the empty means and fully filled means there won't be any colors. Magnetic property, 4f1 to 4f13, they will have unpaired electrons because 7 subshells are there, right? So 7 directions are there, orientations are there, so which will have unpaired electrons. And magnetic moment, the complex calculation, spin plus orbital contributions are there. Just diamagnetic, which are all F40, sorry 4f0 and 4f14, which are all diamagnetic. Sometimes they will give you the atomic number or electronic configuration, ask you to calculate the magnetic moment of lanthanides or actinides also. Talking about the chemical reactivity, they are highly electropositive, react with water to form lanthanum hydroxide. It tarnishes in air, reacts with halogens to form lanthanide halides. And M3+ state is predominantly want to be an ionic, but there are less possibilities of forming a complex with this. The complexing ability increases slightly across the series. And talking about the uses, mish metal, this mish metal, what are the elements are there? That question were asked once. Okay, so just take a look on it. What are the elements present over there? And cerium oxide, that is used in glass polishing, and gadolinium is used in MRI. And lanthanides are very good catalyst for petroleum cracking and pollution control. Talking about actinides, which is very similar to lanthanide. The questions were also asked very similarly, like a magnetic moment, how it is stable, and what are the irregularities or exceptional cases we have. In that, the question can be asked. The oxidation state varies from +3 to +7 oxidation number for actinides, mainly +3 after plutonium. The maximum oxidation state increases till the middle, and neptunium, plutonium, then it decreases. It do exhibit +3 and +4 oxidation state also. Similar to lanthanide contraction, actinide also shows the contraction because of the poor shielding of 5f orbitals with a greater magnitude. Okay, that will be more shielding than the lanthanide. So actinide contraction is more than the lanthanide. It shows more irregularities, variable in because of the variable filling of 5f orbitals. And then color of the actinides, it shows more intense colors than the lanthanides because of the FF transitions are less forbidden. In case of lanthanides, that was more forbidden, but still FF transition happens. But here that is happening less forbidden. Magnetic property, it can form a complex too. Paramagnetic in nature, 5F1 and 5F13. Chemical reactivity, which is more reactive than lanthanides because of smaller 5F orbital extension. It usually does an oxidation. It reacts with boiling water to form actinium hydroxides. It attacked by the HCl but not by HNO3. With HNO3, it forms a passive layer, passive oxide layers like we saw in aluminum chromium. In complex formation, greater tendency than the lanthanides because of their smaller ionic radii and higher charge. Radioactivity, which is very important in case of actinides. All actinides are radioactive. This is a statement-based question. And thorium, protactinium, uranium are naturally radioactive. And some elements are short half-lives they have. This is an entire comparison of actinides and lanthanides. You can take a note of it or take a screenshot of it, pause and note it down, whatever you want to do. Okay, let's go to the last chapter but most important chapter, that is coordination compounds. In coordination compound, we have n number of questions were asked. Each paper at least that will have 1 or 2 questions. So those marks are guaranteed if you are thorough with the coordination compounds. So coordination compound, before talking about that, we have double salts. So what are double salts means? Like we have more salt, which will have the ions in it, like ammonium sulfate and iron sulfate with H2O, that will dissociate fully, completely. Like sulfates will form, ammonium and iron will be formed. But in case of coordination compounds, it will not dissociate completely. Okay, inside this sphere that will remain intact. So if I'm taking any coordination compounds, let's take a general, let's take K4 FeCN6. Okay, these are the important terms. The outside one, which is counteracting the charge on the coordination sphere. So this square bracket refers to a coordination sphere, and the number over here, this is coordination number. It varies. Since Cn minus is a monodentate ligand, straightly we can get it. But if that is a bidentate ligand, tridentate ligand, you have to multiply it with what? Denticity. Okay. So mostly the coordination number will be +4, +6, like that. And metal present over here, that is a central metal, and the ligand, which is called the cyanide or these negatively charged compounds or nucleophiles. Okay, here we have 3 important theories. The first one is Werner's theory. Werner's theory, in the short, I have given you the primary valency, that is ionizable, that's present, which is outside the ring, outside the sphere. Okay, and the secondary valency, that is our coordination number, oxidation number. So which are satisfied by the ligands. So as you can see here, COCl3, 6 ammonia. Here 3Cl is my primary valency and 6 is my secondary valency, that is coordination number. Okay, which takes up the octahedral geometry. So there are many types of ligands like monodentate, bidentate and polydentate ligands. These are some important ligands I just have listed for making you example, but there are many ligands. At least do remember the ligands which are all in the spectrochemical series. Okay, then chelation. Chelation is the ring formation by the polydentate ligands, like EDTA can form the ring, or nickel DMG will form a ring kind of thing, which is in cage formation. Okay, which will give you the more stability to the complex. Okay, the second one, that is VBT, and the third one is CFT. Before getting into that, let's discuss about the isomerism part. Okay, so isomerism, so these are some ligands classification, anionic, neutral and cationic. I have given an ambidentate ligand, ligands with 2 donor atoms but only 1 bonds at a time, like nitro, cyano, SCN. These are some ambidentate ligands. Then chelate ligands, which will give you more stability, I told you. Then effective atomic number, EAN means, EAN is just a nearest to noble gas configuration. After doing this calculation, that should have a nearest to noble gas configuration. For example, let's take this one, CONH3 6 times 3 plus. Okay, what is the formula? Z minus oxidation state plus 2 into coordination number. Okay, so Z, what is the atomic number of the metal? Gopal, that is 27. Minus oxidation state. What is the oxidation state? To know that, you have to know what type of ligand that is. Okay, this is a neutral ligand. The charge is 0. So the oxidation state is 3 plus. 27 minus 3, that is 24. Plus 2 into coordination number. Here I have 6. So 6 into 2, 12. So 12 plus 24, that is 36. Which is the nearest noble gas configuration, krypton? So which where the complex is more stable? EAN rule, if the complex obeys this rule, then that becomes more stable. That is the principle. Okay, if that is not obeying, if that is coming as 35, 34, then the stability is less. Nomenclature, positive part must be named first, then comes negative part. The ligands within the complex, which are alphabetically ordered, and prefix di, tri, tetra, penta can be used for the complex ligands. This just with the parenthesis we have to mention, with the bracket we have to mention. For example, let's see some ligands, some complexes. CONH3 6 times Cl3. Look at the ligand first positive part. Chlorine and a coordination sphere. Which is positive? Of course, the coordination sphere. So, which should be named first? Hexa, amine, cobalt, 3. 3 is an oxidation state, chloride. Then, in the second example, I have potassium and the sphere. Which clearly we can see potassium is more positive than the sphere. So, that should be named first. Potassium, hexacyanide. If the ligand is present inside the ring, that is a negative ligand, okay, anionic ligand, then that should be in with a do. Cyanide means cyanido, nitrate means nitrito, okay. And then ferrate. Ferrate, the complex itself that is negative in charge, that should be end with 8. Okay, cobalt-8, ferrate, zinc-8, like that. And the oxidation number in the end. If they didn't give you the neutral one, if they have given the positively charged complex or negatively charged complex, mention it as an ion. Okay, ion 2 ion. Then we have this diamine chloride of platinum 2, and here you look at this tris ethylene diamine chromium 2 chromium 3 chloride. Okay, so then comes isomerism. First, structural isomerisms. In structural isomerism, we have ionization isomerism because of the ionization sphere that changes. Look at here, I have sulfate in the outside and the another isomer of that, the sulfate goes inside, bromium comes out, right? Which is red violet in color becomes red in color. And other examples are also given. Look at this, changes. Okay, these are ionization isomers. Then second one is hydrate isomers, occurs due to the exchange of the ligand with water. Like, look at this one, H2O 6 times, which is inside the sphere, and Cl3, which is outside the sphere, which can be written as H2O 5 and 1 Cl inside the sphere and 1 H2O outside the sphere. Okay, so this type of isomers are hydrate isomers. And the next one is linkage isomers, which occurs due to the different donor atoms are there, like an ambidentate ligand. Right, so nitro, nitrito, so one is attached with oxygen and another isomer will be attached with nitrogen. So which is a linkage isomerism. Then coordination isomerism, where it occurs due to the exchange of ligands between cation and anion, like this. So this is one complex and PTCl4, that is another complex. So there will be a difference happens on the interchange of the ligands happens between the anionic part and cationic part. And coordination positional isomerism, it's not much important, but the polynuclear complex, it changes. Then stereoisomerism. Take a screenshot of it or get it from the notes. Geometrical isomerism, which is having coordination number 4 and coordination number 6, I have separated. And in tetrahedral, I don't have any geometrical isomerism. Only have in square planar. That too in these states, like MA2, that is having 2 geometrical isomerism, cis and trans, and MA2BC, that is having 2, and ABCD having 3. Then coming to octahedral, ABCDEF 15, this is 9, 6, 5, and this becomes 4, 3, and this is important. A3, sorry for the typo, A3B3 type. This complex is more important because that is not having cis and trans, this is having facial and meridonial. So that facial will form a complex of faces of the triangle like that, and the meridonial which will not have that. And A3B2 type, and A6 which will not have any geometrical isomerism. Talking about optical isomerism, I have MAA2A2, that cis form is optically active, trans form is optically inactive. And in square planar, ABCD has 2 optical isomers, AB2 has 2 optical isomers, and AA2, that is having 2 optical isomers, and trans are optically inactive basically. Then valence bond theory. So in valence bond theory, we have a simple rules. Let's have it with an example of that. Basically, in valence bond theory, they have already predicted so many things. Okay, they have an assumptions. They have lot of assumptions in valence bond theory. Okay, so first of all, if they are giving you a complex, they already assume that is paramagnetic or diamagnetic. Okay, for example, let's take nickel Cl4 2 minus. Nickel, which is in +2 oxidation state here, right? So 3D8, 4 is 0 now. 2 becomes 0 now. Before that, organ configuration will be there. So if I'm filling the electrons, 1, 2, 3, 4, 5, 6, 7, 8, right? And 4 is, that is empty now. But I want to occupy 4 chloride ligands over here. And what they have assumed is that this is a paramagnetic compound. Paramagnetic compound means that is having unpaired electrons. So which definitely will lead to these 2 electrons are untouched, right? So the incoming electrons will come and occupy in 4s and 4p orbitals, right? So which makes the hybridization as sp3. So sp3 means it is tetrahedral complex, right? And similarly, they have n number of assumptions in valence bond theory. They have predicted that is para or dia, and then coming to the configuration, these steps. Okay, that is drawback of valence bond theory. The correct magnetic moment of the complex cannot be theoretically measured by the valence bond theory, and this theory does not offer any explanation about the spectra of the complexes and the color of the complexes. And to overcome these drawbacks, we have this CFT. CFT is very simple, but before getting into CFT, we have to understand one thing. In CFT, they have arranged the ligands in the series of increasing their strength. Okay, so that is what spectrochemical series. Okay, so the spectrochemical series in CFT, that's super important. We have I minus, Br minus, S2 minus. Okay, and then the higher ones which are strong field ligands means we have this carbonyl, cyanide, amines, sorry not amines, this nitro groups, and amine is also one of the strong field ligand, but not as much as cyanide. But that series which is important to predict the structure or geometry of complexes through CFT. Okay, so this is the overall chart of CFT. First of all, what happens? The d orbital, which is having 5 orientations, right? dxy, yz, zx, and dx square minus y square, dz square. Right. So as soon as the ligand is approaching the metal, this is getting excited, and half of it, in case of octahedral complexes, half of it, like dx square minus y square and dz square, goes above, which will have more energy. And these three, xy, yz and zx, that will have lesser energy. Okay, the above ones in octahedral we call it as EG, and the below ones, which are called T2G. Okay, here comes the spectrochemical series important. So some of the ligands are till D4 there is no problem. Till D3 there is no problem. After D3, the ligands are whether that have to stay in the T2G level or going to EG level is decided using spectrochemical series. Okay, if the ligand is strong field ligand, then that will do the para. If the ligand is not strong, then that will go to the higher energy orbital. Okay, and these two are separated from the center, that is called barycenter. From the center, the above ones are 6 dq and the below ones are minus 4 dq. Minus is because that is decrease in energy. Okay, and for tetrahedral, I don't have this EG, T2G, just I'll have E and T2. And also, look at this, I'll have this value ulta. T2 goes above and E goes below. That is the main difference between tetrahedral and octahedral. Square planar, they won't be asking in main, they may be asking it in JEE advanced. Okay. And here in CFT, we have to know few more things, few more formulas about CFSE calculation. So how we can calculate which is more stable? In that case, we have a formula of minus 0.4 into number of electrons in T2G plus 0.6 into number of electrons in EG. Okay, so if you are getting the positive value or negative, you may get positive value or negative value, that decides the nature of the complexes. And also the another relationship is that del tetrahedral, that is equal to 4/9 of del octahedral. Factors affecting stability of the complex. The values of the stability constant KSP differ widely depending on the nature of the metal ion and the ligand. So in general, we have a higher charge density of the central ion, greater the stability of the complexes, and more basic ligands, then there will be greater ease with the which can donate the lone pairs of an electron, and therefore the greater the stability of the complexes. So these are some factors which affect the stability of complexes, and the chelating ligand, as I told you, that is much more stable. Other than chelating, we do have this, I told you, this synergic bonding, right, or back bonding, that is particularly for our carbonyls. Okay, so carbonyl, obviously that will first donate the electrons to the metal, and after that carbonyl is having an empty orbital, right? So after this donation, metal will also donate the electron to carbonyl, like a return gift. So that is how the relationship becomes much more stronger over here. Metal and carbonyl bond is becoming closer. This bond length becoming closer. Okay. Other than this, in these are the critical formulas and concepts for this D block elements and coordination complexes. Some application oriented question can also be asked over there. Okay, so these are the very high important concepts for JEE Advanced from whatever we have seen till now. And in addition to that, some questions can also be asked. We'll see when we are going to solve the JEE Advanced papers. For now, these topics are super important for JEE Main. So if you find this interesting, find this kind of marathon works for you, let me know in the comments. We'll create one more for physical chemistry and organic. By that time, practice more and more questions. Let us know what you want.